In lesson 4.5, we'll be looking at inverse matrices and then some uses of inverse matrices. We see up here we use inverse operations to solve algebraic equations. So if we had something like 3x plus 2 equals 17, the way that we would solve this, 2 is added to our term with the variable. So in order to undo that addition, we use the inverse operation of subtraction. And we have 3x equals 15. And then to continue solving this, this is 3 multiplied by x equals 15. So in order to undo multiplication, we use division. And we get x equals 5. Similarly, we can use inverse operations to solve matrix equations. So here we're going to look at the multiplicative inverse matrix. So the multiplicative inverse matrix of an n by n matrix, so it has to be a square matrix. So the inverse is denoted by A with this little -1, and the superscript is an n by n matrix such that matrix A multiplied by its matrix, or the inverse of a matrix multiplied by a matrix, is equal to the identity. Now we remember the identity is a square matrix that has ones in the main diagonal. So here's a 3 by 3 identity. But an identity matrix has ones in the diagonal, everything else is zeros. So I mentioned this already, only square matrices have an inverse. So we want to determine if these two are inverses. Well, by this definition up here, if we multiply these two together, we should get the identity matrix if they are inverse matrices. So let's go ahead and write these two. So we have 2, 5, 1, 4. And we're going to multiply that by 4/3, -5/3, -1/3, and 2/3. So I got some fractions in there, but shouldn't be too bad. Let's give this a try. So in order to multiply matrices, remember we use the first row with the first column. So we do 2 times 4/3. 2 times 4/3 is 8/3. And then 5 times -1/3. So remember, first row with first column. So 5 times -1/3 is -5/3. And remember, for this, our goal is to multiply these if they multiply together to give us 1, 0, 0, 1, because we need the identity matrix. And now we'll go to the next part, 2, 5, so our first row with our second column. So 2 times -5/3 is -10/3. And then 5 times 2/3 is +10/3, and that will give us that 0. And now we need to do the second row with each column. So 1 times 4/3 is 4/3. And 4 times -1/3 is -4/3. So again, we definitely see that's going to be 0, which is what we want. And then the last one, 1 times -5/3 is -5/3. And 4 times 2/3 is 8/3. And this does, in fact, give us what we need, that identity matrix, because 8/3 minus 5/3 is 3/3, which is 1. We already mentioned this is 0. And this one is 0, and -5/3 plus 8/3 is 3/3, which is 1. So these are, in fact, inverses. So yes, they are inverses. Now what we want to do is we want to be able to find an inverse matrix, not just determine if two matrices are inverses, but given a matrix, we want to find the inverse. It's a pretty easy process. So if we have some matrix A, B, C, D, its inverse is 1 over the determinant of A. So remember, determinant of A is just AD minus BC. And then it's multiplied by this matrix here, which it says D, -B, -CA. And what you can notice here is we switch these two. So in our original, it's AD. Well, so you're going to switch those two, and then you're going to make these two, B and C, you're just going to do the opposite, whatever they are. So let's do a couple practice problems here. So we want to find the inverse of this matrix. Actually, I should mention, notice here, and we should know why this is true, the determinant cannot equal 0. The determinant can't equal 0 because you'd be dividing by 0. So you cannot find the inverse of every matrix because if the determinant is 0, there's no inverse, in which we might run into something like that. So let's do this one. The inverse of x is going to equal 1 over the determinant. So that's 3 times negative 5 is negative 15, minus negative 2 times 7 is negative 14. So sometimes you end up getting a fraction in here, but this will end up being negative 1. And then we're going to multiply that by this matrix where you switch these two. So negative 5 here and 3 here. And then you make these two the opposites. So this is positive 2 and negative 7. And then you write this in the most simplified form. So this is 1 over negative 15 plus 14 is negative 1. And we have our matrix here. And obviously this is negative 1. If this were something like 1 over 21, maybe we would leave that out here, but since this is just equal to negative 1, we can multiply it, do a scalar multiplication to this matrix. So this is negative 1 multiplied by each element in here, which will just change all the signs. So this is 5, negative 2, positive 7, and negative 3. And there's the inverse of x. A way to check that, you could multiply this matrix by the original, and you should get the identity of 1, 0, 0, 1. All right, let's find the inverse of y. To find the inverse of y, we want to do 1 over the determinant, and that's 12 times 1 minus negative 2 times negative 6, which is 12. And right away here, you see we have 12 minus 12 in the denominator, so the determinant is 0. And so this, we say, is not invertible. We cannot find the inverse. Okay, here's where we're going to use inverse matrices to solve some matrix equations. And again, this is a lot like what we've done in just regular solving linear equations. If we had 4x equals 16, we could multiply both sides by the inverse of 4, which is 1/4. Now, the actual proper way to solve it is if we multiply 1/4 on the left side of this blue part. So I'm talking about just left side of the equation, and it's called a left multiplication, so 1/4 on the left of 4. I should do a 1/4 on the left of 16. We don't have to do that when we're solving linear equations because multiplication is commutative, and we can switch the order, and we could have just written the 1/4 out here. For matrix multiplication, it is not commutative. So when I put an inverse of A to the left here, I have to put the inverse of A to the left of C. And so we notice here with matrix multiplication or solving matrix equations, A times X equals C. This is going to be like a coefficient matrix. This is going to be a variable matrix. And this will be a constant matrix if we're working with systems of equations. And in order to solve for X, you simply multiply both sides by the inverse of A. So X is always equal to the inverse of A times C. So in this example down here, we have, this is kind of our A times X is equal to C. So all we need to do is find the inverse of A and multiply it by C. So over here we'll find the inverse of A. Remember from a couple minutes ago, the inverse of A is 1 over the determinant of A. So that's 7 times 3 is 21, minus 4 times 5, which is 20. and then we're going to multiply it by, and we switch 7 and 3. So 3 will go here, and 7 will go here. And then we make 4 and 5 negative. So negative 4 and negative 5. So this turns out nice. This is just 1 over 1, which is 1 times whatever our matrix is. So we got 3, negative 4, negative 4, and then negative 5, 7. So again, in order to solve this, x is going to be equal to the inverse of a, which we just found here, 3, negative 4, negative 5, 7 times c, which is negative 10, negative 6. And so we want to multiply these. We have 3 times negative 3, negative 4 times negative 10, 6. So 3 times negative 10 is negative 30, plus negative 4 times negative 6 is just positive 24. And then negative 5 times negative 10, don't need a line there. Negative 5 times negative 10 is 50. And 7 times negative 6, so plus 7 times negative 6 is negative 42. And so we get a solution that x is equal to negative 6, 8. And so we were able to solve this matrix equation. So if we put negative 6, 8 in for x, we can multiply these and we would get negative 10, negative 6. Example 4 says use a matrix equation to help solve the following word problem. The sum of twice a number and a second number is 8, while 3 times the first number plus twice the second number is 13. So we just have a simple kind of a number theory question here. The sum of twice a number, so 2 times a number, and this is a sum, and a second number, so let's just call it y, is 8, while 3 times the first number plus twice the second number is equal to 13. And so it says solve using a matrix equation. And so what we do here, if you remember, and if not, we have a little review here. We can take our coefficient matrix. So we would want a matrix of 2, 1, because 2, coefficients 1 here, 3, 2, times our variable matrix, which we can just call x or xy. So matrix x is just going to represent our variables of x and y. So we'll just put a big X there, equals 813. And so in order to solve this matrix equation, we're just going to multiply both sides by the inverse. We can think of this as our A, X equals C. We're going to multiply both sides by the inverse of A. So we want to find the inverse of A, which is 1 over the determinant, which is 2 times 2 is 4, minus 1 times 3 is 3, which this is just 1. So our inverse is actually just going to be what's inside this matrix. And we flip 2 and 2, which is really easy to do because they're the same thing. And then we make these two negative. And so since we're multiplying by 1, our inverse is just this part right here. And so in order to solve this, we have x is going to be equal to the inverse of A, which is 2, negative 1, 3, 2, multiplied by C, which is 813. And so let's go ahead and do this multiplication. 2 negative 1 with 8 and 13. 2 times 8 is 16, plus negative 1 times 13 is negative 13. And then 3 times 8 is 24, plus 2 times, I made a mistake here. This should have been a negative 3. I think I said it, but I never put the negative 3 there. So this should have been a negative 3, which won't change my first row because it had to do with 2, negative 1. But this would be negative 24, and 2 times 13 is 26. And so we get that x is equal to 3, 2. Now, we use this to solve a word problem here. So what does this x equals 3, 2 mean? Well, coming up here, we said x, our matrix x was just equal to our x value and our y value here. So our first number from the word problem here, the sum of twice a number, so that first number is 3, and the second number is 2. And we could check that over here. 2 times 3 is 6, plus 2 is 8. 3 times 3 is 9, plus 2 times 2, 4. 9 plus 4 is 13. And so there is the answer to that word problem.